Friction horsepower is the power consumed by an engine to overcome internal friction and drive auxiliary components like fuel pumps, exhaust systems, and other moving parts. This power loss due to friction can account for a substantial percentage, roughly 10 to 15% of the indicated horsepower in modern aircraft engines. The indicated mean effective pressure, IMEP, symbolizes the average pressure generated in the combustion chamber during the engine's operating cycle, representing the frictionless power, i.e. the indicated horsepower. IMEP doesn't account for frictional losses or the actual power delivered to the propeller shaft. To understand the friction loss and net power output, consider the indicated horsepower as comprising two powers, one consumed by internal friction, friction horsepower, and the other producing useful work at the propeller, brake horsepower. The portion of IMEP that yields brake horsepower is referred to as brake mean effective pressure, BMEP, while the remainder used to overcome internal friction is known as friction mean effective pressure, FMEP. These concepts, though theoretical, aid in understanding friction losses and net power output. Despite lacking physical existence in the cylinder, BMEP and FMEP serve as useful representations to set pressure limits and assess engine performance throughout its operational range. There's a direct relationship between IMEP, BMEP, and FMEP. The pressure developed in the cylinder during combustion is a significant limitation on engine operation. Controlling this pressure is crucial to prevent dangerous internal loads that could lead to engine failure. Hence, determining these cylinder pressures is essential for safety and efficient power application. BMEP can be calculated using the equation BMEP equals bhp x 33,000, length, where bhp is brake horsepower, L is stroke length, A is the cylinder bore area, N is the number of cycles, and K is the number of cylinders. For example, if given values for bhp, stroke, bore, RPM, and number of cycles, substituting these into the equation allows us to determine BMEP. Thrust horsepower is the result of engine and propeller collaboration. If a propeller were 100% efficient, thrust and bhp would align. However, propeller efficiency varies due to engine speed, altitude, temperature, and airspeed. Thus, the ratio of thrust horsepower to bhp delivered to the propeller shaft differs. For instance, an engine producing 1,000 bhp with an 85% efficient propeller would yield 850 thrust HP. Among the discussed horsepower types, it's the thrust horsepower that determines the engine-propeller combination's performance. Efficiencies. Thermal efficiency. Engines and power rely significantly on heat as their primary source. The heat generated by burning gasoline in cylinders results in rapid gas expansion, moving pistons and creating mechanical energy. It's known that mechanical work and heat are interchangeable, having a fixed relationship to each other. Heat can be measured in work units, like FTLB, besides heat units. The British thermal unit, BTU, measures heat, being the heat needed to raise 1 pound of water by 1 dgf, equivalent to 778 FTLB of mechanical work. When 1 pound of petroleum fuel burns entirely, it releases about 20,000 BTU, which equals 15,560,000 FTLB of mechanical work, reflecting fuel's energy in heat and work units. Thermal efficiency, the ratio of useful work from an engine to the fuel's heat energy used, is crucial. An engine with higher thermal efficiency delivers more power from the same amount of fuel. Additionally, higher thermal efficiency means less waste heat to engine components and lower fuel consumption for a given flight distance and power. About 25–30% of the heat from combustion contributes to power output. 15–20% is lost through cooling, 5–10% in overcoming friction, and 40–45% through exhaust. Improving thermal efficiency involves reducing friction, improving combustion efficiency, and reducing heat loss. Compression ratio greatly influences the portion of combustion heat converted into useful work. Higher ratios increase this conversion but also elevate cylinder temperatures, leading to rapid material deterioration and fuel detonation. The formula for indicated thermal efficiency is IHP x 33,000, weight of fuel burned min, x heat value x 778. Brake thermal efficiency uses bhp instead of IHP. For instance, an engine producing 85 bhp, consuming 50 pounds of fuel at 18,800 BTU per pound for 1 hour, yields a brake thermal efficiency of 0.23 or 23%. Reciprocating engines are around 34% thermally efficient, converting only a third of fuel heat into mechanical energy. The rest is lost through exhaust, cooling, and internal friction. This thermal distribution is illustrated in Figure 142. Mechanical efficiency. Mechanical efficiency. Mechanical efficiency measures the power delivered to the output shaft compared to the total power generated by the cylinder gases. It's represented as bhp/ihp, with bhp being the useful power to the propeller shaft and ihp the total developed power. Typically, the difference between bhp and ihp is the friction horsepower, FHP, lost in overcoming friction. Engine friction has the most impact on mechanical efficiency and remains relatively constant across the engine's speed range. Aircraft reciprocating engines often achieve around 90% mechanical efficiency. Volumetric efficiency. Volumetric efficiency, expressed as a percentage, compares the volume of fuel, air charge inducted into cylinders, corrected for temperature and pressure, to the total piston displacement. Factors like atmospheric conditions affect departure from 100% volumetric efficiency. The U.S. standard atmosphere sets temperature at 59 degrees and pressure at 1469 lbin2, establishing a standard density. Engines operating below this standard have less than 100% volumetric efficiency, while those with true supercharging may exceed 100%. The formula for volumetric efficiency is volume of charge, corrected for temperature and pressure. Piston displacement. Several factors influence decreased volumetric efficiency. Part throttle operation, long intake pipes of small diameter, sharp bends in the induction system, high carburetor and cylinder head temperatures, incomplete scavenging, improper valve timing, propulsive efficiency. Propulsive efficiency measures the effectiveness of converting brake horsepower, bhp, into thrust horsepower, TP, by the propeller. It's the ratio of THP to bhp, where TAP is approximately 80% of bhp. The remaining 20% is lost in friction and slippage. Optimizing propeller blade angle ensures maximum propulsive efficiency across various flight conditions. During takeoff, a low blade angle maximizes thrust at low speeds, while high-speed flight requires increased blade angle for maximum efficiency. Constant speed propellers adjust to maintain required thrust efficiently across different flight conditions.